Hello everyone, I'm Yifan from Wuhan University. Today I'd like to present our work of robust and scalable Gaussian process regression and its applications. Now let's begin with introduction. Gaussian processes are the dominant method for inference on latent functions. They underpin a wide range of algorithms for regression, classification, and unsupervised learning. However, a well-known limitation of the Gaussian observation model is its sensitivity to outliers in data. A few outliers can drastically destroy the entire posterior regression result. This hinders the real-world applications of GPR for many domains, where outliers are often inevitable. This work intends to conquer the GPR with outlier-contaminated data. Specifically, we present a robust GPR model, which uses variational learning and is less likely to overfit. We also leverage inducing variables and SVI to adapt our model to large-scale data. We further describe two applications of our model, that is, feature matching and downstream expression imputation. We next show our proposed method. We explicitly consider the generation process of outliers. Since outliers are independent of the latent function, a reasonable assumption is that they obey a uniform distribution, so the likelihood is the mixture of two models. As a robust GPR problem, we place a GP prior over the latent function and suppose the mixture coefficient follows a beta distribution. After incorporating the above prior distributions, the full joint distribution is obtained. However, the exact estimation is analytically intractable, and thus approximation is needed. To this end, we use the variational inference to approximate the exact posterior. We introduce a variational posterior distribution in which that the KL distance between the posterior and the variational distribution is minimized. We further partition Q into disjoint groups using mean field factorization. With this factorization, the maximization of lower bound is obtained by optimizing each of the factors. The above bound in mean field factorization can be optimized using the coordinate ascent technique. We have derived closed-form expression for every factor updates. Sparsing introducing variables approximation and sophisticated variational inference can be easily applied into our variational framework, extending our model to large-scale data. We next introduce two real-world applications for our robust GPR model. The first application is feature matching, which aims at establishing reliable feature point correspondences. To this end, we first construct a putative correspondence set by nearest neighbor matching and convert the putative set to a motion vector set. As we can see, the motion vector field is slow and smooth and can be described by GP. Thus, we use our model to determine the correctness of each data and preserve inliers as correct matching. With the help of SVI, our model finishes the matching in milliseconds with almost no mismatches. The second application is downstream expression imputation. Recently, technological advances have made it possible to measure spatially resolved transcriptional mRNA expressions with spatial information in tissue samples. However, due to the equivalent mode functions and the process turbulence, the readout data may contain bad spots. A Valence GPR may lead to completely wrong results and thus mislead the subsequent analysis. By comparison, our robust GPR copes well with the outliers and is able to give meaningful imputation results. Here, we show some experimental results of our method. We first conduct numerical experiments. Some visual examples on near data are presented. As we can see, our method still works well in face of 80% outlier ratios, despite all other methods have failed. In addition, our method is able to approximate not only the posterior mean, but also the posterior variance. In other words, our method is able to give almost the same posterior GP in face of outliers to exact GPR on inliers. The quantitative results also show that our method has significant advantages. For feature matching experiments, we show several visual examples on Y-FCC dataset. As can be seen from the bottom line, our method is the fastest and has the best performance compared to recent state-of-the-art methods. The quantitative results also show that our method performs the best. For dense gene expression imputation experiments, we stacked the original spatial transcriptomic imputed results to show the quality of the imputation. As we can see, the imputation results of exact GPR are very different from the original spatial transcriptomics. This is because the outliers heavily disrupt the inferred results. In contrast, our method is robust enough to give accurate imputation results, which facilitates downstream analysis. The quantitative results also confirmed above conclusions. We further analyzed the proposed robust GPR algorithm. We found that our method generalizes well and can handle different outlier distributions. In addition, our method is very fast and can easily scale to large-scale data, especially when equipped with SVI. In the end, we summarize the contribution of our work, which is threefold. First, we present a robust GPR model, which uses variational learning to approximate the true exact posterior. Second, we leverage inducing variables and SVI to adapt our model to large-scale data. Third, two applications of our model are described. Extensive experimental validation demonstrates the superiority of our model. Our code is also publicly available and can be accessed by scanning the QR code. That's our work. Thanks for watching.